Now we're going to move on to global class field theory. For class field theory over Q, we look at finite abelian extensions of Q. Now for global class field theory, we look at finite abelian extension of a number field K. We want to generalize the key theorems in class field theory over Q for this context. To be more specific, we want to generalize Kronecker-Weber, Artin reciprocity, and Dirichlet's theorem on primes in arithmetic progressions. To that end, we need to generalize the notion of the ideal class group and also Z mod MZ star. We will also need a generalization of the notion of cyclotomic fields, as well as that of conductor. Then for Artin reciprocity, we need a generalization of the Artin map and also a generalization of its kernel. So let us start with the generalization of the ideal class group and Z mod MZ star. Yes, the good news is that there is one object that generalizes both of these. Let us start first by defining the concept of a K-modulus. Loosely speaking, a K-modulus is just a formal product of finite primes and infinite primes of OK. So what are infinite primes? Well, for every real embedding, say sigma of K into R, we will attach a formal symbol, P sigma, and we'll call that an infinite prime. So we can think of infinite primes as real embeddings of K. A K-modulus then is the formal product of an ideal of OK with some infinite primes of OK. Now, given a K-modulus, we can associate to it a Ray class group defined as follows. Remember, in the case of class field theory over Q, we relate the Galois group of L over Q with the ideal class group, with a generalized ideal class group, right? So the Ray class group here is a generalization of that notion. So just like in that case, we define IM to be the group of fractional ideals of K that are relatively prime to the finite part of M. And then again, similarly, we define this Rm to just be the group of fractional ideals, principal fractional ideals of OK, generated by elements A in K star such that A is congruent to 1 mod M. Note that here, by congruent to 1 mod M, we mean that, first of all, the order of vanishing of A minus 1 at every prime P dividing the finite part of M is going to be greater than or equal to the order of vanishing of this M naught at P. And then at all the infinite prime, A is going to be greater than 0. What that means is that under these real embedding associated to these infinite primes, the image of A is going to be a positive real number. Alright, so if we let Rm be the group of principal fractional ideal generated by these A that are congruent to 1 mod M, then that's a subgroup of this Im. We can take their quotient, this is called the Ray class group, modulo M. Now, let us see that the Ray class group is indeed a generalization of both the ideal class group and Z mod MZ star. So let's start first with the ideal class group. Here we choose the modulus M to be 1. In that case then, I1 is just going to be the group of fractional ideals of K because there is no restriction. Similarly, R1 is just going to consist of all the principal fractional ideals, and so C1, being the quotient of the fractional ideals over the principal fractional ideal, is just going to be the ideal class group of OK. Thus, the Ray class group indeed generalizes the notion of the ideal class group. Now, let us show that it also generalizes Z mod MZ star. To that end, let us assume that K is Q, and let's choose our modulus to be the product of some integer M with the infinite prime corresponding to the embedding of Q into R, the natural embedding. Observe that when K is Q, then the fractional ideals of K just corresponds to elements of Q star, i.e. the units of Q. With that identification, we see that this group Im of fractional ideals relatively prime to M just gonna consist of quotients of integer a over b such that a and b are both relatively prime to M. And then Rm is just gonna be the group of principal fractional ideals a over b such that a is congruent to b modulo M, And A over B is gonna be positive under the embedding of Q into R. So that just means that A over B is positive. Now the ray class group in that case then would just be the quotient of this group of A over B, AB relatively prime to M, with A over B that are congruent to 1 mod M. And this is clearly isomorphic to Z mod MZ star under the map sending A over B to AB inverse modulo M. Right, observe that the kernel of this map just consists of the fractions A over B such that A is congruent to B modulo M. Thus we see that this ray class group notion generalizes both the concept of the ideal class group and also the unit group of Z mod MZ. Next up, we want to generalize the notion of a conductor. And then using that, we're gonna generalize the notion of cyclotomic fields. Finally, that will allow us to generalize Kronecker-Weber and describe all abelian extensions of a given number field K.